Good evening everyone, and welcome to the monthly Beyond Zero Emissions discussion group. Firstly, we would like to acknowledge that we're meeting on the lands of the Kulin Nation and pay our respects to their elders, past and present. We'd also like to thank the University of Melbourne Energy Institute, the MEI, our Zero Carbon Australia project partners for this great venue, even if the door was locked. For those of you that haven't been to one of our discussion groups before, Beyond Zero Emissions is a climate change solutions think tank and research organisation. We research solutions to all of Australia's greenhouse gas emissions and assemble and publish the solutions and communicate them. Our projects include Zero Carbon Australia research, Repower Australia talks, media work, education programs and much more. We're always looking for more volunteers, so come and talk to us afterwards if you'd like to get involved. This discussion group is a forum for climate change solutions with presentations by experts in their field and is held on the first Monday of every month, usually. Tonight, MagEfekt is an Australian engineering consultancy who have developed revolutionary manufacturing techniques to offer the most robust range of purpose-built lithium-ion batteries in the market. MagEfekt specialise in designing, building and manufacturing battery packs to meet specific customer requirements right here in Melbourne. MagEfekt aims to produce energy-dense batteries for both mobile and stationary applications. Engineer Andrew Lamb is a battery technology expert and we're delighted to hear about the topic that everyone is talking about, battery storage. Would you please welcome Andrew?
Okay, thanks for coming. Thought we could come in today and the two options were to sell you something, put a brochure out there, put it in front of you, but that's all on the website. So I'd encourage you all to have a look at the website. We do all sorts of things. The project originally started because a friend builds wheelchairs and he wanted to put a lithium-ion battery in a wheelchair. So that's where I got involved in making batteries other than my previous projects we'll get into a little further on. This is our main product at the moment. That goes into a wheelchair. We're very happy with it. It seems to sit around for 2 years on the shelf without needing any tinkering, and it's about 2 years before you have to look at it for balancing. So it's a 3,000 cycle, 10-year life of wheelchair battery. We've run a few wheelchairs with it. We're in the stage of building up to go out to a full trial. We're hoping to get 40 wheelchairs out there in the field, working with Swinburne and a local manufacturer to do that. And of course at the end of the trial we'll hopefully get sign off to be able to put them into wheelchairs. Okay. So I'd like to go through a little bit of material tonight, and I want to challenge people here. I want to challenge you to think differently. I keep coming across people who think batteries are a storage of energy. The only thing that goes into a battery and out of a battery is amp hours. Your energy is something you may use. You may get the batteries out, but if you start thinking in amp hours, you'll get a better feel for a battery and you get better efficiency of from what you're doing. And it also explains why you get a better efficiency out of lithium than just the energy density. Okay, and I'll get into that a little further down the track. Okay, most of your applications require amps. You're going to run an electric motor up a hill, you require amps. Most of the time it's not volts. Volts is a limit of a device. So if you think about your customer's needs in terms of a wheelchair, you need to get up that gutter, you need amps. Volts is the top speed on a wheelchair, volts is the top speed in an electric vehicle. Okay. Most of the time we look at the data sheet. The data sheet describes the product. It doesn't describe what you want to do with the product. So think about the customer's needs rather than the data sheet. Make it safe and make it reliable. Okay. Battery is a chemical cell. It has two potentials. You push it backwards and forwards by ingress and egress of amps. You can recover the amps. If you're not recovering the amps out of your battery, something's wrong. You need to start checking things, checking for leakage, condition of battery, your electronics in your electricals. Okay. Voltage. It's about 200 years since Volta did his work and defined what voltage is. He described it as potential, and that's what it is. It's the potential you can get out. Voltage is an activation energy for an LED. If you pulled up behind a car and you can see some blanked out LEDs, the volts isn't getting to that LED to turn it on. There's a voltage threshold that the LED will turn on. Above that voltage, it does nothing more until you get to the point where you actually wreck the LED. Now, the ones that are blanked out, generally sturdy connections, and it drops off. You have a bit of resistance, you drop the voltage, it won't turn on. And I'm sure you'll notice it on the way home tonight, now that I've mentioned it. Okay, your top speed of an electric motor is determined by your volts. That's when the back EMF of the motor balances out with the voltage in your battery. So it starts and spins up. You very rarely get to the top speed. Very, very rarely do you get to the top speed. Now your voltage is also the point at which your device arcs out. It can be a diode, it can be a motor that punches through the insulation on a motor, or even insulation on wires. Okay. Now, putting batteries in perspective, you may have sat in a Tesla out at Chadstone. There's a couple agencies out there. So if you're looking at your customers' needs, your capacity of your electric car is about the equivalent of a Coke can full of fuel. So if you start thinking about it in that perspective, a very big battery is a very, very small fuel tank. And it's very important to understand how it comes together. You can see over there, lithium's right at the bottom. It's tucked right away in the corner here, even though it's about 4 times lead acid. We're down here. Look at where diesel is. Look where petrol is. We're out the top there. And within the lithiums, you've got a whole range of technologies. Now, we've gone down a particular path for reliability and safety, and I'll get to that a little bit further down the track. But think about it in terms of a Coke can. Okay, here's some of your lithium technologies compared to lead acid. Now, we've gone with lithium-ion phosphates, which is not 4 times the performance of the lead acid, but we are getting 4 times the performance in our application in the wheelchair. And there's good reason for that. Okay, this is our wheelchair. This is where we started. Friend makes these. He has a couple of clients. They want to go out all day. If you live in a wheelchair, you want to have a bit of adventure. He could do 10 kilometres at 10 kilometres per hour. He wanted to do better. Well, we got him better. We got him 40 kilometres at 10 kilometres per hour with about 60% of the weight. In fact, if we filled the thing up, we get him 80 kilometres at 10 kilometres per hour. And it has occurred to us to enter a few guys in a marathon just for the hell of it. Okay, very good wheelchair, by the way. It's Magic Mobility, made here in Melbourne. Very robust and serious. He does climb on sand with it and go up hills. It's a great little toy. Now, getting back to what I was talking about, amp hours. That's a typical curve for a lead acid battery. Now, you can assume at the top of the curve here, depending on the temperature of the day, about 13.5, 14 volts, right at the top. Drop down, and you come all the way down, and this maybe 12 volts, maybe 10 volts. It's your application limit. So, in the wheelchair's case, 10 kilometres per hour. That was our application limit. And that's the shape of the curve. So if you're a potential energy guy or an energy density guy, everything under this curve, right the way down to 0, is your energy density. There's your lithium. That's your lithium curve, typical lithium curve. Okay, now we're up here. If the wheelchair wasn't speed limited, you might be 14, 15 kilometres per hour. We want a 10. We started at 10. We travelled along 10, we held 10. Okay. All that area there, just wasted energy. Doing nothing. It's getting chopped, PWM controller down to DC motor does nothing. It's just amp hours out. Okay. And there it is. That is what you lose with your LEDs. Now, to give you a little bit of an idea of practical application. There it is. We made up a prototype. The first battery we put in the wheelchair just to see how it went. I picked up some Panasonic packs I had, applied the principle to it, take that off, does exactly the same job. I've just sliced a chunk off the battery. That original battery pack was designed to fit in with the lead acid profile. So they wanted the same charge threshold as you would with a lead acid. Piece of history. It's just a habit. That is what you would normally do. Now we've got to try and get this back. Blank, blank. And computer. Is it moving? No. HDMI. There we go. All right. So we got 4 times the performance out of our initial battery. This is our latest generation battery here on the bench. This is the sort of battery that goes into the wheelchair. This gives us 4 times the performance of the lead acid in that application because of this curve. This is where your benefit is coming from with your lithiums. This is why amp hours are important. If this is your voltage, your working voltage, you say, what do I want when my tank is empty, when my battery is empty? I want to be here. You don't need to be here. You don't want to be there. That's just all wasted energy. So the beauty of the lithiums with a very flat charge profile, discharge profile, is you don't waste that energy. Now there's other tricks you can do to try and pull back that energy in the LEDs. Very complicated. LEDs are great for keeping fishing boats in the water. Per weight, fabulous in terms of recycling. Big heavy lump of lead, you take them down to Laverton, they recycle them, they make a fortune out of recycling. It's a nice clean bucket of chemistry. But it's not so good if you're wanting to make a vehicle out of it. Okay. So this is important. Torque gets you up a hill, voltage turns on an LED, anything above what your job is a waste of time. Now, it's also really important to think about current when you're talking about solar panels. And if people want to talk about maximum power points on solar panels and managing those, I'm happy to talk about them later and why lithium batteries are so much better coupled to a solar power system than a lead. And it's because you have a tighter variation between your discharge state and your charge state. Makes your electronics a lot simpler. Okay. Now, people have needs. And I've given a talk on a couple of occasions about motor vehicles. I'm a motor vehicle guy. I spent 20 years in the automotive industry and 15 of those I was also making solar cars at night. And it comes down again to people's needs. These are not my cars, but I have similar vehicles to this at home. My daughter's into horses, tows. You need something very grunty, a lot of torque to tow with. I've got a Prius model before that. I drive that everywhere. I've actually got a tow bar on my Prius. You can tow around your lunch and a picnic basket. Very light tow bar. Occasionally I tow a 14-foot laser, which you can pick up in one hand anyway. And I've also got a red inside at home. Interesting vehicle. The numbers are about right. I was getting that driving from Frankston to Port Melbourne, consistently out of the Prius. That's taking Beach Road. Very, very economical. But this comes down to customers' needs. It's the same thing as when you look at the wheelchair. What are your customers' needs? They wanted more than 10 kilometres at 10 kilometres per hour. What are your needs? Who would drive this stuff? Okay, so normally we call that family in tow. It's a big vehicle, your caravan, your horse float. Your Prius is typically your family car, and your commuter car to get to work. 1.1 occupants. Okay, who would have one? Who needs one? Okay. Well, it's interesting. According to the Australian Bureau of Statistics, your rush hour occupancy is about 1.1 in a vehicle. Okay. How many houses in Australia, suburban, fully detached houses, have more than one car? In fact, they have as many cars as licensed drivers. Well, it's about 3 million. Okay. The automotive fleet life in Australia, about 10 years. Up to 14 some years, between 10 and 14. If we replaced an electric vehicle and built them all here, you're talking 300,000 vehicles a year you could build here. That's more than we've ever built in Australia. So it's a big market, it's big options, so it's really important to get that efficiency, and let's face it, batteries are expensive. So if you're thinking about your voltage, you're thinking about your amp hours in and your amp hours out, you get to start cutting down the size of your battery. Less battery, less price. Less battery, less weight. Less weight, greater efficiency. Right. Okay, now, domestic. There's a couple aspects about domestic that are important. What do we need? Yeah, great. You want to run an element heater and I just bought a house and it's got one of those IXL Tastics you turn on and you can fry an egg underneath it, and you've got the, sucks the steam out of the bathroom. Not the greatest thing in the world to have if you want energy efficiency. Heating and cooling your house. A friend just put solar onto his place and he got the worst grid feeding tariff. So he also wanted an air conditioner, so he times his air conditioner to come on when the solar's available, and he just burns a lot of his energy through temperature control in his house, and it's a nice steady temperature when he gets home. Think about your whole house as a battery. It's a thermal battery, it's a thermal bank. If you let your house get stinking hot or freezing cold during the day, waste of energy. You'll find that your air conditioners, they like to have a nice cool source outside to dump heat into and a nice warm source outside to get heat out of. Their efficiency drops off greatly when they're pushing harder. So also that works in, you've got the electricity, you put your high efficiency split system in, the house works great. That's the best bang you can get for the buck in each domestic situation. So it becomes really important not to say, I'm going to put a Tesla battery wall up there and I'm going to have all of this power and I'm going to pay tens of thousands of dollars for my battery backup system, and you go, well, I'm going to replace it with LEDs, I'm going to put some insulation in, fix the draft here and run my air conditioning during the day to stabilise the temperature. Bring down your energy consumption, bring down the size of the battery. Let's make it more realistic what you actually need. Dishwashers, washing machines, all those sort of things can be done on timers. Okay. Now, we try and make batteries. Now, we make batteries very well. People keep asking us to put them in things. So we form partnerships with other people. Now, this particular one we built, that's pumping sewage down at Rye. They've got to put sewer systems through all the areas that traditionally had septics. Okay. And you've got to pump them. You can't run them downhill. To pump them, you've got to have masticating pumps, and you can't have one pump and then the other pump, because that just pumps from pit to pit and it doesn't pump it all in the same direction. So these are coordinated pumping systems. And another chap I know said, look, could you build us one? Now, we just wanted to sell him batteries, but he wanted us to build the whole thing. So we built the whole thing. We got onto a chap up past Hillsville that helped us out with that, and we've got other people we work with to put them in. So if you ring us up and you look at the website, I want to fit something to my house or my factory, we have people who do that, and we keep pulling back to do batteries. We're concentrating on batteries. It's working faultlessly. We do not put a BMS on these batteries. Now, you do not need to put a BMS on a battery if you know what the battery's going to do. These batteries are in the bottom here, no BMS. Now those batteries should last about 2 years before they need any attention at all. We'll go down there at the 18-month mark, have a check on them, we'll go back at 2 years, we'll balance them then. Then we'll come back in another 18 months. Now your batteries traditionally need balancing because they have internal leakage. That's a quality indicator. If you control your quality, you get it all balanced out, the batteries go up together, they go down together, you do not need a BMS. When I took my package out of Holden, I went round to people I knew, said, give me your failed batteries. Number one killer of batteries, BMS. Solid state electronics leak. Solid state electronics, as you get them hot, they leak more. A hot day can cause a PNP junction to go on. Open circuit will come on. They will leak by temperature. So you may be perfectly fine when you build the thing, you put it out, it's in its tin box, in the sun, stinking hot day, it starts to leak. That will kill your battery. If you've got a BMS through there and it's connected, you can discharge a section of your battery and kill it. Then, of course, you're trying to compensate for that and it becomes a situation of chasing your tail. Now, we also look at safety. This is where we get a bit into the chemistry of what's in there. So we really specialise in building packs. There's a lot of people researching the chemistry out there. We also look at predictive health on batteries. Now we have a project where we're looking at developing a predictive health analysis, which is live, and we'll look, that's something for further down the track. So we've got a stockpile of around about 600 failed batteries we're working our way through. We're about halfway through it. So we're progressively analysing it, we get people's batteries in, we tear them down. We have a look at why they failed, we quiz them to the application. Okay, so we're all about reducing the battery failures. Now, mentioned safety before, we've gone with a lithium-ion phosphate. Our batteries don't get hot. Well, sorry, our batteries could get hot if we worked them hard enough, but you design them properly, they don't. Our battery packs don't get hot. If you've got a battery pack that is getting hot and your cells should not be getting hot, you need to raise a question about your battery pack. I bought a little non-contact thermocouple, cost me $45. I walk around, look at electrical systems and I measure the temperature. If anything is getting warm, it has resistance. If it has resistance, you've got some problems. So we check all our circuits, and if you're building an electric car, putting in the solar system, you've got a hot spot, you need to look at it. $45 on eBay. Brilliant investment. I didn't buy it for this, I bought it so I could pick up which cylinder of a Ford engine was missing. And that too is indicated by temperature on the exhaust manifold. Okay, we look at things like eddy current. Eddy current in batteries. Very large arrays of batteries have gone to eddy current. Now, when you think about the bigger your battery, the more energy is in there. If it was to go to an eddy current, that's a lot of energy to dissipate. So you have to question why. Why would it go to an eddy current? We do an integrated fuse in ours. We also grid them. So if you were to get a large battery array from us, you'd find they're in a grid pattern. Every block is connected to every other block, every parallel section is connected to every other parallel section. But the current that can flow between parallel sections is limited. And that's not very complicated, that's just a resistor. Love to take credit for that one, but no, we found that in a tear down of a North American pack. That's one good thing about it, there's a lot of bad things about it, so we decided to pinch the good thing. Okay, thermal runaway. Lithium-ion phosphate has a thermal runaway of 270 degrees C. If our high dependency client patient is sitting on their wheelchair, they're a high dependency patient. They cannot get out. You don't want thermal runaway. Lithium-ion phosphate is the highest thermal runaway temperature we can find. Very, very important. The reason we fuse them is if somebody cuts through our cables, shorts them out, will require quite a bit of talent, blow a fuse inside the battery. You want it in a bus, you want it in an electric car, we'll also grid it, but each battery will have a fuse in it. So you'll know all about it when you have a problem. Fuses are reliable to an extent, but when they blow, your failure mode is it stops. Not a great failure mode for a high dependency wheelchair, because that wheelchair will stop. It'll stop dead. But better than the alternative. We haven't had a failure yet, by the way, and we have no plans of having a failure. Okay, that's what happens when a battery fails. I built that battery pack, unfortunately. I also built a lot of that car. Right, that was 40 parallel modules of 5 cells. Sorry, actually, I think it was 7 I put in that car. It took me 6 months of work to figure out why it caught fire. Okay. This is very early in the piece. We used to monitor the battery end to end. We had an open circuit failure within one of these satchels. Wouldn't have thought it. Why on earth would a cell open up inside? Took me a while to find that too, but essentially I was building another pack and I found one. Found the production process too. Staking process between 2 different metals. It's done inside the battery. That process failed. So when you do a battery, you need to look at the durability of it. When you do your own joints, whether it be clamps on lead acid batteries, dry connect, push connectors. I have bolts, by the way. I do use them, but reluctantly. Never put bolts through a circuit board. The circuit board relaxes as the bolts become loose, and it will become a resistor, and eventually it will catch fire. This is what happens with the Vectrix. It also happened on the back of a locally built alternator when they didn't torque up the nuts properly. You'll actually heat up the cables. So very important to have quality connections. Your torque is limited by the materials you are torquing. In this case, it was a staking operation. Didn't work properly. The circuit opened. Going back to it, we were measuring across the pack, and we couldn't see the fact that that had opened. So one section was overcharged, gassed up, thermal runaway. That was a lithium polymer pack. That's the pack that replaced it. Re-engineered the pack. They're a satchel pack. They have their own problems, but for the racing purposes, they're very good. That had a book value of $3.5 million when it went up. Came back in a bucket. That was in Spain. Magnesium casing on the wheel motor at the front. That caught fire, burnt a hole through the road. Hot summer's day, bushfire, water bombing helicopter. Very spectacular. Yeah. Well, what do? You push the envelope. This is what you get out of it. Okay. Other failures you will get in batteries, lithium-based batteries. It's debatable what's going on, but you've got a polymer film. You'll have a certain amount of defects per square metre in a polymer film. The bigger the cell, the higher the probability you will have a defect in it. You'll find some of your vehicle manufacturers use 18650s. We're using 26650s. We do not use plastic bags. Essentially, the plastic bags are like a wine cask, and the failure mode for the satchels for water ingress, I found out of an article or a paper on wine casks. Water gets through the membranes. Water reacts with the lithium, swells them up. You'll see lithium's gas. You'll see the Thunder Sky plastics. Plastic lets water in. They also gas and swell, and you'll find that. The steel cans, they'll gas and swell, the square ones. I've never seen a square balloon. Things want to be round. Nice round steel can. 26650s, 18650s, very good. Getting back to this particular failure mode, 2 arguments. One is there's a hole in the membrane. There's normally 3 layers in the membrane. They reckon electrolyte concentrates in the membrane. Yeah, maybe. There's also another explanation. Whiskers. what you'll find is metallic whiskers will grow where there's preferential current density. And you'll find those, if you look up metallic whiskers on ICs, you'll get some good stuff on the internet about it. We had a case in Bosch where we had a solder whisker grow around a diode, away from a diode, and it short-circuited the diode. Observation was made many years earlier by highly capable scientists there, and took a while for us to figure out what was going on. And it was the whisker growing through the bubble in the lacquer. We got rid of the bubbles, we got rid of the problem. Now, I happen to think that that particular failure mode is possibly a whisker growing through the hole in the plastic. Now that shorts out and leads to a short circuit through the film and the failure of the batteries. Okay. Thermal runaway again. Okay. We're looking at about 3,000 cycles on our battery. That's full cycles, that's the lab test. That's 80% capacity we're expecting at the end of 3,000 cycles. Part of our target for the wheelchair is life of chair. It represents about 10 years. These high dependency patients, they'll have that chair for 10 years. You don't have to replace the battery. All of a sudden you're not looking at the chair. We need a service regime because we're now no longer servicing the battery. Got to look at the tyres, the bearings, the switches, everything else in the chair. Considerable saving. We're hoping to get through our testing and end up, we'll stretch those NDIS dollars a little bit further. A little more health dollars. That should more than pay for itself. Okay. All right, reliability. Why do batteries fail? Design defects. Plastic satchels aren't good for keeping water out. You thermally weld the outside of them, you pinch the inside of the battery. They're not very durable either. Coercive currents. Leakage through solid state on battery management systems. The leakage through devices. When mobile phones came out, we're fitting them to cars, and all of a sudden we got a lot of complaints at Bosch the batteries were going flat. That was the mobile phones. They were draining the batteries. A lot of energy going through the batteries. So one of the big bogeys for any car application is coercive current. That's why that little light glows in your plasma TV. It's where a lot of your energy goes on your electronic devices. You switch off a room in a house, you cut down the amount of power you're going to use. And that's critical if you're going to put in your battery wall. It's critical if you're going to size your solar system. So it's really important to understand where your energy's going. Your battery management system failures. I've seen a lot of cracked capacitors, ceramic capacitors. Many years ago I was asked to see if I could pass on the liability to the component manufacturers. I could not buy a ceramic capacitor rated to go through the reflow oven. It was designed to be soldered through a reflow oven. Couldn't buy one. So we had to do a lot of work on balancing the temperature on our reflow oven so that it wouldn't thermally shock and crack the capacitors. So very, very important, that one. Ceramic capacitors do fail by cracks. They are a common cause of short circuits in BMSs. You can get whiskers growing around ICs, you can get mechanical failures as well. Membrane defects, water ingress. Any battery with a valve will let water in. Warm it up, quench it, it'll suck water straight through the valve. I don't like the steel square batteries or the prismatics in plastic or steel with the valves. I can make them gas. You want to try it, warm it up, put a bit of water on there, suck it in. If you want to try a membrane, a bit of water in a syringe, squirt it in the side, watch the battery swell. Reacts very quickly. Okay, poor manufacturing. A lot of manufacturing defects. You'll find there's very few manufacturers of the components that go into a lithium battery. You can buy a production line, turnkey, and there's a lot of manufacturers. You want a quality manufacturer. One of the telltale signs, if you can twist their arm to do it, is sequential numbering on the cells. If you're numbering every cell, you're monitoring your production, you get a failure, you go, geez, mate, that was done after the tea break. So what happens over a T-rack? You go back and you fix your problem. And the one that affects most of us, poor application. Okay. Poor application can be an undersized battery pack or an oversized battery pack. You want to operate your lithium battery in that nice flat area of the curve. You want to stay away from the drop off, from the steep rise at the end. You want to look after your lithium battery pack. We put buffers on, depends on the application as to how big a buffer we put on. We ask a customer, what are you using it for? We go out, we visit them. We might sell you exactly the same battery with completely different amp hour ratings. That's because of your application, and we'll back the usage off at either end of that battery. And that'll determine the life. If you're going to abuse the battery, if you go beyond the point, of course, you'll kill something. Okay, bigger's not better. Okay, bigger membranes in your battery, bigger cells, bigger membranes, more likely to fail. So you're buying batteries, you're buying lithium, don't go for the biggies. That's a lot of lithium, a lot of investment to have fail. And this is why your Volt, your Tesla and your other manufacturers use 18650s and 26650s. You look at it and go, why? It's a cell, it's a little cell, it's a couple of bucks. You can check it, you can throw it away. You try and drive a nail through this pack, it'll bounce off the cans. Nice steel can, a little bit of a plastic washer at the top, very little opportunity for water to get in. And of course you won't get water past our casings anyway. So the bigger the membrane, greater likelihood of failure. Okay. Your prismatics, as I've said before, if you've got a nylon casing, nylon likes 3% water. Take a nylon stocking, you put it in an oven, you dry it out, rub it in your hand, it goes to powder. It fractures. Nylon needs water. I'll put nylon features into electronic housings to desiccate the inside of the electronic housings. Great valve. And I built them in. I built a Harley-Davidson regulator with 2 nylon blocks at the back for pumping water out of the regulator. Worked a treat. I came across it. Originally we had a remote keys. We sold from Clayton, we sold remote keys to Porsche, and they would die. But we only sold the electronics. They put them in an acetyl housing. Acetyl takes 0.3% water. Yeah, we had the boys dropping them into the washing machine and they were surviving. Turned out that nylon is great at sucking up water. Steel cans, fantastic at keeping water out, provided they don't have a valve in them. Okay, that's why I don't like the prismatics in there. The satchels, water goes through the outside. It's a polymer skin, water will go through that. You get a metallic film in it. If the metallic film was perfect, yeah, you might keep the water out. Normally it's not. And the manufacturing process requires you to breach the metallic film to weld the sides of the plastic prismatics together. So the 18650s and the 26650s, they're our preferred. We may get back to the plastic satchels as we further refine our encapsulation and just rely on our encapsulation. But at the moment, we're on the steel cans. Now, that was the last solar car battery pack I built. There's LiPo. I left that out overnight. That was a very expensive pack that we built, and SAFT. You can see all the modules. There's a lot of batteries in there. It ran perfectly for 2 years. We had a battery room which was essentially an explosion-proof bunker. Went to check the battery, left it out, went home, condensation developed on the pack, went through the plastic liner and swelled up the cells. Trashed the battery. Now, a bit of another item on that. We built a battery monitoring system. That battery pack, because it's a racing pack, was bottom balanced. Take all the cells down to the bottom, balance them out, bring them up. because of careful selection of the cells and good quality, they went up and down, up and down, up and down for 2 years without deviation. In fact, it was perfectly good before I left it out. And I only left it out in a factory. There was no rain, it was just atmospheric condensation. The wiring, that all went to optical couples. So there was actually no electrical connection between the battery itself and the monitoring electronics. It was all done through photons, through crystals. Plenty of of that. Perfectly comfortable doing it because everything was unplugged when it went on the plane. The parallel section was designed such that if you did get a short circuit, there wasn't enough energy in a parallel section to burn the rest of the pack. And that's pack design. Okay. Now, we do a lot of things with our batteries. We have a lot of people ring up. We had one chap ring up. We do a lot of charity type work. And this chap was looking at putting solar power into East Timor. And he came up with a series of problems. Now, one of the problems was he reckons the batteries would get pinched. We're about to start doing some further refinements and we think we can submerge this in salt water. Water gets in at the end of the cables, that end. It's the only point water can get in. There's no vacuum inside the battery, there's no gas, there's none of the swelling as temperature goes up and down. We may end up burying these batteries. So if we go to East Timor, dig a hole, bury them, we're worried about it, pour concrete on it, run a couple of wires out, balance it every 2 years. Bit of maintenance on it. Yeah, a couple of people might be persistent to dig them up. They leave them in there for 10 years, absolutely abuse them, don't maintain them. Yeah, you've got a little bit of a fire 2 feet underground. I don't think that's going to cause a problem. Okay. Now, our shelf life is 2 years. Look at the data sheet and the quality lithium battery. It'll tell you the same thing. We're all about getting the same out of a battery pack as you will out of your cells. I told one guy recently that he said, "What's good about your batteries?" And I said, well, our performance is the sum of its components. If you're putting a battery pack together and you are not getting the sum of its components, you need to ask why. Okay. We don't balance them when we build them. We're careful about how we build them. These things run cold. Go back to your battery spec sheet. Have a look at what it says. If you're building a battery pack, it's getting hot, and your data sheet says it shouldn't get hot. Ask why. We're impact resistant. The wheelchairs are interesting. The current specifications for wheelchairs consider that somebody's going to pick this up, they're going to carry it over to the wheelchair and they're going to drop it. We put as much material on this battery as you require. You want to drop it out of an aeroplane, you can drop it out of an aeroplane. Just a little bit bigger. It's a nice rubber casing. Make it as thick as you want. Also, if it does split, which is highly unlikely, we haven't frozen it, but it should be good down to -35. So we are talking about some very cold places. You drop it out of an aeroplane, it cracks, so what? There's nothing to spill. It's going over. You have a crack in it. Yeah, eventually that would cause water ingress. It may corrode some of the inside of the battery, most likely to be the connections rather than the cells themselves. So it's impact resistant. We don't have still air in there. Still air is the best insulator you can get. That's the theory behind your pink bats. Your expanded polystyrene foam, it's not the material, it's the air. It's holding that air still as the insulator. You'll see a lot of batteries on the market where they have lots of air gaps. Even some stuff I've read recently where they submerge the batteries in oil, silicon oil and circulate to get rid of the heat. Ask the question, why do you need to get rid of the heat? Where's your heat coming from? Okay, so given we don't have any air gaps, we have a relatively high thermal diffusion. We also structure them for thermal diffusion, but we can't seem to overheat them. So we'll blow the fuses before we overheat them, and we refuse to apply the battery outside of the manufacturer's specifications for the cells. Somebody cracks open that fuse, replaces it with a dead short and goes off and does something silly, we can't do much about that. That's customer abuse, but we just make it hard for them. We are thinking about a clear potting resin to make it hard to pick out that fuse. We're looking at 80% of capacity at 3,000 cycles. The issue you've got when you put them on a house is how many cycles do you have? We've got one on an abuse trial at the moment. We've got about 20% of the appropriate battery capacity on a house. The thing's just going up and down, up and down, up and down. Very much an accelerated test. And it actually powers our manufacturing turrets on a house and runs into the manufacturing plant. It's running cold. But we're counting how many cycles it goes up and down. We should achieve the 3,000 cycles long before regular use. So the things we won't give you the detail on are the things that we've put all the work into. It doesn't have electronics in it. We've gone with the lithium-ion phosphate because of its reliability, because of its thermal runaway temperature. 270 degrees C, that's well above radiator temperatures in a car. If you look at the lipos, you look at the other lithium technologies, we're talking about the sort of temperature you will get under the hood of a car from the radiator, not the exhaust from the radiator. Things you would instinctively pull your hand away from if you touched, but you wouldn't necessarily suffer third-degree burns. Okay, so that's pretty well what we do. We're a small, virtually start-up company. We do consulting. Our consulting is really based around understanding the client's needs. Sometimes we just consult. There's lead times on projects which are big. We keep getting asked to put in installations, and we farm that out to people we think are good at it. We're working with other companies and other teams and universities. We're out there to learn, and a lot of what we do is all about learning. So that's us. David Trainer's one of the founding members of MagEfekt is over there. You can ask him all the hard questions. Max Coulthard couldn't be here tonight. He's tied up giving lectures down at Monash. So there you go. Any questions?
You mentioned turnkey production line that you can buy. Do you have a production line yourself?
No. We figured that, check the back of the couch, we don't have $20 million down there.
Right.
Also, everybody else is doing it.
Sorry?
There's a lot of people doing it in China.
Right.
Okay, it'd be nice to bring it into here. There's two sources of lithium in Australia, spodumene. One's privately owned in WA, and I believe they've sold the marketing rights to a Chinese-based company. So to get the material in, you'd actually be buying all the components in from China anyway and assembling them.
Right.
So you can't buy your inputs. So we'll buy the cells. We'll concentrate on building the packs. The gap we see at the moment is the packs. We'll wait for other people or use other people's talent for the cells.
Thank you.
With bottom balancing,
Yes.
does the pack have to be out of service during balancing?
Yes. For racing, there's a lithium polymer pack which has a shorter life, and of course we just push the hell out of these things. But you can imagine you're going along the road, and it's the same question in your electric car. You don't care that your tank's full, you know it's full. But when you get into the end of your tank, you care when it's going to be empty. You don't want surprises on that fuel gauge. For those who have owned a VZ Commodore before, or many other cars, it's a real pain to calibrate the bottom of the fuel gauge, and we used to get lots of complaints that the car ran out and it wasn't quite on the E. So we just crank up the adjustment on it. So the bottom balance, bring them down, make sure they're at the same rate, good quality pack. You fill them up. In the case with the SAF packs I was building, they all went up together anyway. But if they're old or they're a lesser quality pack, when your first parallel module is full, your tank's full. Take the energy out again, provided you don't leave it on the shelf forever, or it has a defect in it. Of course, it'll come down predictably and it'll be empty at the same time. Last thing you want is one module to get to be empty first. because you'll push it past the state of recovery, you may gas it, you may catch it on fire. And yes, I've done that. Sometimes deliberately, or at least that's my story.
You've quite surprised and alarmed me with your comments about dangers of moisture and moisture ingress.
Yes.
So I have an electric push bike which I keep in the garage, and sometimes I get caught in the rain and stuff. How worried should I be then?
Dry it off, keep it in a dry part of the garage. If it's got satchels on it or square cells, yeah, look, depends on what's in it. If you've got an 18650 or 26650 can, I wouldn't be too worried about it. If you've got plastic satchels, keep it dry. Take the battery out, put it inside. I've used kitty litter before. Kitty litter is great. You know, put it in a bag with kitty litter if you're worried about it. Normally what happens with a prismatic, a rigid prismatic or a valve on top, is a certain amount of gas in there, gets warm, gas comes out. Cold really quickly, it will suck through that valve and that'll suck water in. I put a whole lot of batteries in my hothouse. When I sort of niggle towards what's going on, and you look up your galvanic series and you go, okay, what could be going on here? Put them in the hothouse. Geez, they failed quickly. Nice and humid, spray water on them. Then I've got the needle, diabetic needle, put it in, just, and that's that expanding. And what it is, it's the moderator, the graphene or the graphite, and it just swells up and you open it up and it wrinkles. But I might have a picture of a wrinkly one there. Oh, I think I might have taken it out. Okay. It's not very good, but you can see the black medium here. You'll get them in a pack and that'll be wrinkled down the side. And you get them gassed up. I had people that would insist they could recover batteries, and I have put holes in those plastic membranes, let the gas out, and crushed them between clamps. And you can get the current flow back. They'll never be any good, but you will get the current flow back. Emergency situation, yes, I'd do that, but other than that, no. So for your electric bike, keep it dry. You should be keeping them dry anyway. So.
Does that lithium-ion battery have memory? Should you charge it up and decharge it fully?
Quality one, no. I haven't had that problem with lithium iron phosphate, and I haven't had it with lithium polymer. So, you know, not got a memory.
I was just thinking about what you're talking about there with the moisture. So in the rainforest, you need different packaging to what you do down here in Melbourne?
Well, I killed that leaving it out in the factory in Clayton. Wasn't a leaky roof. It's just humid day, chilled out overnight, dampness everywhere, died.
So have you done installations in Cairns or other tropics? Or?
No, we're Melbourne based. We're slowly growing. As I said, we think we can put that in salt water.
Is that rubber?
Sorry?
Did you say that was a rubber shell?
A rubber.
A rubber.
A rubber. It's an elastic polymer.
I was going to say, yeah.
It's not rubber, it's not gutta percha. Sorry, you were...
We're looking at electric bus services.
Yes.
It's the minibus for that. Most electric vehicles seem to have fixed battery situations where we're looking at battery exchange. Is there a problem with that? Because you don't see much.
Yeah, look, what you've got to look at is what is going on in my circuit. And if you're going to have anything that plugs and unplugs, connectors fail. Connectors get worn. The housings, the retention pins, they'll fail. You need to actively monitor the characteristics of your system to look for that failure. So I wouldn't recommend having an exchange of a battery. If you look at the numbers, if you optimise, you're probably looking at a big charge overnight, small charges during the day would actually negate the use of a battery. If you want to run interstate, you need to question why you're trying to do something Sorry, I'll digress for a moment. Right. When I did my talks on what the customer needs are, I did a little piece on the internal combustion engine. Okay. If you go through Gippsland, you'll find every 5 miles there's a micro town, or there was a micro town. That was the distance that you could ride your horse into town, pick up groceries and ride home again. The internal combustion engine has changed that. Everything we do, how often we shop, how far our food comes, is a product of the internal combustion engine, the size of our house, our garage, our expectation. It's all the internal combustion engine. So I'll get down to... No, I'm going the wrong way. It's a different sequence to what I'm used to. Okay. Getting back to this one here. You pull up at a service station, doesn't matter whether you're using diesel, petrol, kerosene, doesn't matter. Put that nozzle in the tank. Your energy transfer from the petrol pump to your vehicle is about a megawatt. That's a lot of energy. You're probably talking Loyang could run the equivalent of a couple service stations the size of the ones in bottom of the Westpac Bridge. Electrical energy is very, very expensive. When you look at battery way down here in the corner, petrol way up here, and what are you doing with it? 1.1 occupants, that's a 2-seater car. If you've got a bus that is a short commute, doesn't do many Ks in a day, you've got good regen on it, and you're getting back that power, you're not getting up the high speed, so you don't care about aerodynamics, you're getting a good transferred mass to massive vehicle ratio, so all your work's not going into just having a heavy vehicle. That's when you get the sweet spot for your bus. You get the big charge at night, and you go, well, I know I can do the middle of my charging cycle. Sorry, I'm getting back here. So I'm going to sit around here somewhere. I can hammer the hell out of them. Just at the top of my head, David, put you on the spot. How many amps can I pump in and out of this thing without breaking a sweat?
Right now, we've probably taken nearly 95 amps out of that.
No, it's in cycle. What's the
Cycle.
Number of cells by 10? What have we got in this?
20, we've got
220 amp?
176 cells.
176 cells, so it's 220 amp. We can pump in and out of that thing all day, every day.
Yeah.
So if you stop with a bus, you're going around a circuit, you pull up, why not charge? You're starting full, you end up with a sawtooth structure. So you're full, you come down, you've got to stop, you come up a bit. You come down, you've got to stop, you come up a bit. In fact, that's how we used to run the solar cars too. You'd fill it up and you bring it down and going down the road, you check your sunshine, you do that. But getting back to your original point, if you're going to swap batteries, you need to be looking for that defect. You need to do your failure effect analysis, understand what the failure mode is for swapping the battery, the connections don't join up, and you've got to hunt for that defect and continuously hunt. And they do get sneaky. I've had Anderson connectors where the blade wasn't quite engaged, and probably about the 5th or the 6th time the connector pushed back past the blade. And I just had a light touch on the blade and it got stinking hot. Now, if you've got an electric vehicle you know, you love, you trust, it's going to work the same all the time. So you're looking for a difference. As soon as you see a difference, you've got a problem. You don't need to know what the problem is, you need to know you've got a problem when you start. Sorry.
After 3,000 charges,
Yep.
you're saying that's 80% capacity.
Yeah, now that's...
Thereabouts. But
Thereabouts.
once you fall off after you reach those 3,000, is it straight line, like...
I don't know. The honest question is I don't know. You get a bathtub curve, initially you get infant mortality failures at production. We get rid of those. They're gone. You solve that problem. You've got a steady state and then you start to get an increase in your failure rate. What you're likely to see is one cell will go before the others. At 172 cells in there, one cell goes quicker. That'll start to drag down the pack. So it's hard to predict. We're building for that 3,000 cycles for that 10-year. We're focusing on that on the wheelchair. Sorry.
What do you guys don't manufacture the cells, do you?
No, we do not manufacture the cells. We select the cells, we assemble them into batteries, and we encapsulate them.
Could you elaborate a bit on the process of how you guys determine which cells, what vendors in the process you have to go through to figure out?
Sorry, the answer to that is no. Look, it's what we've been working on. You want to invest? Yeah, no worries. We'll tell you then. So, offering them got reasonable one. Ben. Yes, do it.
What the battery you put in a wheelchair, that one, is it?
It's actually double the height. It's the same structure. It comes out of the same tool. It's just double the height.
So, I'm a farmer and I'm thinking of putting one in a four-wheeler. What would I...
A quad bike?
Would you need two of those in a four-wheeler?
You still got your petrol motor or just to run electric?
Run electric, yeah.
Oh, okay.
And what would that cost? And what does that cost?
Oh, to be polite, an arm and a leg. They are expensive. Lithium-ion phosphate batteries are expensive. If you've got an application, you're doing it for a hobby or an interest, shoot us an email. We'll put together a quote for you. Certainly, one of the clients of the wheelchairs, he runs a cattle station. He's probably, he wants to be on our trial, but he's so far away we don't want to put him on the trial, but he wants one badly. So if I get an excuse for a holiday, we'll go and visit him. Now, he wants to do his long range, so if we've got an 80k on our standard test, he'll certainly be able to do 40k's hopping over rocks. And you don't want to be out in the bush for 4 hours in the middle of Central Australia. But if you're curious, shoot us an email, we'll give you some prices on it. But that would be the basic. Right, sorry, we had... Yep. All right.
I'm interested in your view on what to do with these batteries and when they come in life.
Okay. Yes, we are working on it. We thought we had it sold at the start. We had an arrangement to send them off to China, and then they put up the Great Wall of recycling. Turned out that a lot of the people who were recycling actually weren't. So we lost our recycler. There's a recycler in Indonesia we were talking to.
You're sending them to Volkswagen?
Yeah, that's another story. But anyway, we are working on it. One of the key things with batteries is it's a big block of chemistry. We know what's in it. The day we send it out, it's the same chemistry. So that if you've got a big block, it's more cost effective to get it back. This is why lead acid batteries are so good. They're heavy. We're only moving them to Laverton for recycling, so they're cost effective. This will be cost effective. I'm yet to track down a good story behind mobile phones. If I can hunt down what is really going on with the mobile phone batteries, then I'll start working on it. And if you look at the Energizer out at the moment, they're saying they build their new lithiums with 5% old lithiums. So that's not very much. Yes, but it is a resource, and we're very interested in seeing where that resource is going to go. While lead acid is very, very dangerous if it's let out into the environment, particularly the sulfuric acid full of lead sulfide, if it goes to the right place and is processed the right way, you get your lead back, you get your sulfuric back, you get your polyethylene back, and you get your glass mat back. Highly recyclable. We should be able to get to a point where they will be highly recyclable.
Do you think that's going to be an issue with the solar storage market?
Yes. Yes, that will become an issue, but there are other issues, particularly around safety and cost. Yes, sir. Sorry, have I answered your question? Yeah.
One of the great moves forward in charging lead-acid batteries is the smart chargers. I'm just saying smart chargers because that's what I use, because they control the current and the voltage, and I'm not quite sure how they work, but they're much better at their job at charging a lead-acid battery and stopping it from sulphiding and all the rest of it.
Yes.
What system do you use when you charge this type of battery? Do you have to use a similar type of charging regime?
Yeah, I've read the papers on the pulsing of lead-acid batteries. I know the chemistry, I know the dendritic growth in the lead-acid batteries and how they fail. I'm not satisfied with that, and I wasn't satisfied when I was doing charging systems either. They do work better than, yes, the other ones, and the other ones are generally cheap and nasty and push hard. The theory with the battery and the principle behind the battery, gentle. Now, one of the things with fast charging is you're in a rush. You don't need to fast charge if you're charging overnight. You can take all the time you want. You push it in gently. It's less than how many power point. It's less peak loading. But what it does is it allows that time for the chemistry to diffuse. And that's really important. You might hear about supercaps. The principal application of a supercap is to take the ripple out of the current going back into a battery, because a ripple will destroy a battery. Now, I've read papers that says my smart charger puts a ripple in to control dendritic growth, and I have a problem with that. I'm not comfortable with that argument at all.
So you're basically saying this type of battery here could be charged with a conventional battery charger?
Yep. Yep, just a nice gentle charger. We put battery chargers on these things. We generally limit the output. We want the client to charge it slowly. In this case, overnight. One of the funny stories we got off our chair partner was a client rang up from Canada saying, I can't charge my chair, And he said, well, where do you leave it? He says, on the veranda. He says, how cold does it get? Oh, about -30.
Yes.
Yeah. Bring it inside, it'll charge. Yeah, so I'm missing.
You indicated the temperature operating range is -30.
No, that's just on the casing.
Sorry?
It's on the casing. When we do, you've got an operational range of a battery. Yes, you'll get a little bit of current out of it at -30, but we designed the casing so it could be chilled to -30. You turn this thing on and you expect to get a lot of grunt out of it. It just won't happen at that temperature.
So what's the normal operating temperature range?
Oh, I can't remember that off the top of my head. David,
0 to 40?
do you remember that?
It's -20 all the way up to 70. 70. That's pretty good.
Do not quote us on that. We will not sell it to you then. Beside the fact, if your chair's at 70, you're in trouble. Yeah, sorry. Yep.
Is there any reason why you can't charge one of those batteries with other batteries?
Well,
Like if you had a solar array on the roof and you're charging a battery, and if you're talking about overnight storage, overnight recharging, I'm talking about this electric bus.
Okay, yes you can. You can dump in there, but what you've got to remember is you've got a battery at a higher potential. You hook the damn thing up, throw a handle, whatever you're going to do, fence. That is going to try and dump into the other. If you put a PWM on it, you chop it, and then you put a super cap on to flatten it out, so effectively you're doing a constraint on it rather than dumping the power through a resistor. Yeah, you could theoretically top up charge with another charge, and I have dumped from one battery to another before for various applications. So, help you?
Yeah, my question is virtually the same, arising from what you were saying. So if you want to have a fully, you take this gentleman's bus, and you want to power up the green energy from solar PV, and you want to grab all that solar energy during the day, so it's not going to be charging it during the night. and you also want to be using that bus during the day, what's the ideal setup to...
You need, look, a bus is a great thing from a, where's it going, what does it do?
Yeah.
They go on a route. They're fantastic for that. You know where they're going to go, you know how they accelerate, you know how they decelerate.
Yeah.
You data log it, and if you work backwards from your route, if you're going to go from here to Sydney in one run, that's not what electric drive's all about. It's about that street circuit. You pull up at the bus stop, sitting here, they keep coming on, they're waiting there, whatever it is now, their pay pass or whatever it is, and trying to buy the tickets. You could be charging.
As long as it's not a MagEfekt.
Yeah. So you could literally top up charge at that bus stop every time it stops.
So every stop you've got solar PV panels there at the stop?
Well, you push it into a battery, but you've got to remember too, if you're running from one battery to another, you're only going to suck down that portion of the battery that is above the battery you're pushing into. So you have to think about that. And of course, then you go through transformer, rectify back to DC and put it in. There's a wonderful thing running around Melbourne called the tram. I really like the way they connect electricity, and that's one of my preferred options for a bus. If you have a bus stop with all the intelligence of the pantograph and the tram contacting, come underneath, it contacts it in and it's charging while you're filling up. The other thing is regen. Regen is fantastic. You accelerate up, you put on your brakes, you decelerate down, you put most of that energy back in. Back when we were doing solar car, very early in the piece, I think we had a silver zinc pack, and with a silver zinc we expect to kill it in a race. It wasn't dead, so what do we do? We go to Sydney. Well, we must have picked the most miserable day possible. Headwinds, cloud. It just shouldn't have been like that. It was between Christmas and New Year. And then we hit the bushfires and smoke. We were running most of the way on 10% solar. We had the, we actually built the motor with CSIRO, the wheel motor. Our worst motor was 98.3% efficient. We got 140 kilometres on regen alone going down the Great Divide. Regen is brilliant. There's a reason your brakes get hot. All that energy is going into your brakes. If you push that back into the batteries off the bus, you hit the brake, it regens, it fills up your battery. So if you recover 80%, that's 80% you've recovered, you don't have to put in. Very, very important. Yes?
I appreciate the lithium-ion phosphate batteries, excellent for small purpose, dedicated applications and that. You were talking about before, what are you using for utility grid storage?
We have been asked to look at that. It comes down to your dollars and your life. They are slowly replacing the Telstra type exchange batteries, and it really comes down to that life thing, and of course the stability of the voltage. If if your requirement is here, most of your energy is available here, and your lead's way up in a low place here. This starts to affect your dollar equation. Also, your leads will throw out, they throw out hydrogen. You can sometimes smell the sulfuric acid out of them. They have a little valve in them. Even the sealed ones have a Gore-Tex valve. If you turn it over, the Gore-Tex will stop the sulfuric coming out. If it gets a cycle of heat and cold, it'll start to push it through the Gore-Tex. So they're not great. If you abuse a lead acid battery, it will throw hydrogen. If you've got an ignition source, hydrogen generally needs an ignition source, but it's a very, very low flash temperature when you light it up.
It's magnificent that we've got Australian engineers doing this sort of research, but have you looked at alternatives rather than lithium because of the environmental impact there? Just to have sort of space on the environment.
We're open to it. We look at it, as I said, I play with lead acid, silver zincs, nickel metal hydrides, NiCads, and of course a range of lithiums. I've just had batteries from everywhere. My Insight 2000, I've got to pull out the the battery pack on that and rebalance it. I just jumped in on the weekend. It came up with the IMA fault. I know what it is. There's an internal leak in one of the sticks in the battery pack, so I pull it out and balance it. They all have their constraints. You are talking about an ionisation process, a wet chemical process in all of them. None of these chemistries are friendly. None of them. Swallow a button battery, you're in trouble.
What about other types of technology like sodium nickel and that sort of stuff?
I haven't played with sodium nickel, but I haven't played with them. You've got to go back again and ask the question, what do you want to do with it? If it's made in volume, if it's you get the quality, you get the price down, you get the portability and the durability and the backup.
Yeah. Small applications.
Well, we are looking at stationary backup. One of the discussions we are having is for a suburb. And there is an equation in that, and you go, well, do I put these in every house or do I put it in the corner? And then you've got your point of generation and what are you going to do with it? And the argument always is, where's my demand? How much do I want to invest in the green energy? And we look at it and go, mate, we want your storage next to your use. As Edison found out, DC is not good for pushing down power lines. His network fell over very, very quickly, and Westinghouse got ahead with his AC. So if we have a bank, we've got to chop it to AC, we've got to run it to the house and then rectify it back with DC. And even when we're doing solar cars, we rearrange the circuit to get the battery and the motor as close as possible, shorten the lines. I don't know what's the best, I don't know what's around the corner, so I can't help you there. So yes?
There was an electric bus, the Brightstone bus, unveiled in Victoria on October 30th.
I did see that in passing, yes.
Goes to Sydney on a single charge.
Yeah. I hear they can go to Sydney on a single charge. That's interesting.
Yeah. That was some business news.
Yeah, right.
And there's also a group, the Transit Australia group. I think they're in Western Australia. They're looking to enter the Malaysian market. So
yes, I'm aware of that.
Non-electric buses. Are they using lead acid batteries, or is there been a big development?
No, look, as far as I know, nobody's using lead acid batteries in mass transport. It's heavy. Heavy is expensive. It costs a lot in energy. The discussions I have, and I can't say too much because I don't know what people put on their websites and in their data sheets, but everybody's using lithium, as far as I know. Your hybrids aren't, of course. Your Toyotas and your Hondas are not.
We can speculate what's going on. Buses, you say?
Yeah, I have seen some working Toyota that, yes, but I haven't seen that on the market.
What's the price is?
I can't remember what's in the back. I did read it. I haven't had it out. It doesn't fire, so I don't have to worry about it. Not like Honda. Sorry. Yes?
Just in regards to the cost of the lithium-ion battery cells, do you estimate roughly the proportion of the cost that's the raw material versus the processing, so like the labour and the machinery, and like what's actually driving the reduction in costs? Is it more efficient manufacturing, like automation, or is it a reduction in raw material costs?
Look, all the above maybe. The problem that we've got at the moment is the Chinese market is not a free market. They have targets, a lot of it is state controlled. There was an overestimation in production. Consequently, solar panels have crashed in price too. They're just not viable for most manufacturers to compete with the Chinese. The same with the batteries. I don't know what the true cost is. I know I'm paying well above what I would like to be paying. And I know there's still some fact in true production costs.
So this should cost as opposed to the...
I'm expecting the price to decrease. One of the things we're doing and why we're doing it is we build the battery packs here because it's becoming increasingly complicated, if not impossible, to ship lithium battery packs. They don't like putting them on planes and they're getting rather hesitant.
Just ask Bowie.
Sorry?
Just ask Bowie.
Yeah. Although we have various ideas about that one too. It looks like failures I've made myself. Right.
I think we're going to have to call it quits there. We're going to get kicked out soon. Thank you very much, Andrew. That was blindly interesting. Are you able to wander down the pub?
Probably not. I'll just check a few things before.
Okay.
Where is the pub, by the way?
Just around the corner.
Head that way. I'll follow
It's
that.
like Nelson Street. Yeah, Nelson Street. Yeah, almost next door. Yeah. Okay, well, for those that want to go to the pub, some of us will. You can catch up on these YouTube recordings and download the slides at VZD website, vzd.org.au/events/discussion group. VZD survives on donations from individuals, not from any industry or politics. So if you'd like to help support VZD, it keeps us independent, and we'd be very happy to hear from you. And with the Paris talks approaching, I'd like to plug for the People's Climate March on Friday the 27th of November at 5:30 at the State Library. The next discussion group is on Monday the 7th of December. The venue is here. Dr. Yasmina Dekesi from Monash University will present on perovskite solar cells, which are the next generation in thin film solar technology, with manufacturing advances making them significantly cheaper than traditional solar cells, silicon solar cells.